Section 2.2 in inductive and deductive reasoning. So the first vocab word is a conjecture. It's an unproven statement, kind of like an educated guess. You watch things, you make guesses about what's going to happen next. So oftentimes they'll say to make a conjecture, that's asking you to make a guess. So this is just a guess. Inductive reasoning. It's using patterns to make conjectures, using patterns to make a guess. So if I said 7, 6, 5, blank, 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 what would be your guess? Well, a really good guess would be 7, 6, 5, 4, 3, 2. That'd be a good guess. However, inductive reasoning can actually be wrong because you're using patterns to make your guess. So actually, 7, 6, 5, 4, 3, 2 is not the pattern I was thinking of. I was thinking of 7, 6, 5, 5, 7, 8. The digits of my parents' phone number. Their area code happens to be 765. Their phone number is not 432. Now, for the record, it's also not 578, but it's a point for the example. Inductive reasoning and educated, it's a guess based off of the pattern that you see. A counterexample is something that proves your guess is actually wrong. So an example, everyone in this class is a male. That's a guess. It could happen. A counterexample, we would need to find someone in this class who is not a male. So if I say everyone in the class is male, you need to find an example in the class that is not a male. So we don't necessarily know everyone in this class, so let's just say Mrs. Yarbrough is in the class and is not male. Now, there are other people that are not male that are not in the class, but in order to prove that everyone in the class is not a male, you only need to focus on the people that are actually part of the class. Deductive reasoning. Using facts, definitions, properties, and laws to form logical arguments. So an example here, let's say 6x is equal to 12. Can you conclude what x is? Well, yeah, you can divide both sides by 6 and tell me that x is equal to 2. So you would say if 6x equals 12, then x equals 2, and this can be proven using the laws of arithmetic. So these are facts, definitions, properties, and laws. These are not just patterns. These are actually proven things where inductive reasoning are just patterns. So law of detachment. If a hypothesis of a true conditional statement is true, then the conclusion is also true. It says this: P arrow Q, P, 3 little dots in a triangle. Those dots mean therefore Q. Now for me, the symbols, I like it because I can read them very quickly and it's a lot less to write. But it might be easier for you to read it this way. If P, then Q, and P happens. We know that P happened. Therefore, Q will also happen. So if it rains, I will go to the movies. It rains. You can conclude that you will go to the movies. You can conclude the part after the then. That's called the law of detachment. The law of syllogism is a little bit more interesting, but also a little more complicated. It says if A then B is true, And if B then C is true, then if A then C. So, P arrow Q, Q arrow R. What can you conclude? It's kind of like a chain reaction. P causes Q, but then Q causes R. So P ultimately causes R. Yes, Q happens in the middle, but the end result is what we care about. So in words, if P then Q, if Q then R. The conclusion, or therefore, if you prefer, if P then R. If P happens, then Q happens. If Q happens, then R happens. The conclusion, if P happens, R will eventually happen. Now, it could also be written on your formula sheet. You'll see it's two different ways. P arrow Q, R arrow P, conclusion. So another chain reaction here, but you have to find the first part of the chain. P causes Q, but R causes P. So what has to happen first? R has to happen first. And if R happens, then P happens. But if P happens, Q happens. Q is the end of the chain. So it could look like this first one, or it could look like the second one. In words, you're going to see two ifs and two thens. So part of this section is finding patterns. So we need to find the next two numbers, letters, or figures in the pattern. So I usually first look at addition or subtraction, then I look at multiplication or division, and then I look for something totally random. So let's look here. From 20 to 19, we subtract 1, so it's minus 1. From 19 to 17, we subtract 2. From 17 to 14, that's minus 3. From 14 to 10, that's minus 4. So what should we do next? We should do minus 5 to get 5, and then we should do minus 6 to get negative 1. B. Let's see here. It's plus 0, plus 1, plus 1, plus 2, plus 3, plus 5. So, plus 0, plus 1, plus 1, plus 2, plus 3, plus 5. And the initial reaction is that I have no idea where those numbers are coming from. There's no pattern there. This is a really famous pattern, though. It's called the Fibonacci sequence. Ignore the plus 0. Look at these numbers. 1, 1, 2, 3, 5. Where are those coming from? 1, 1, 2, 3, 5, 8, 13. 1, 1, 2, 3, 5. They're the same numbers. This should be plus 8 and then plus 13 to get 21 and then 34. The pattern is you take two numbers, the 1 plus the 1, and you add it to get the 2. Then you take the 1 and the 2, and you add it to get a 3. Then the 2 and the 3 added give you 5. The 3 and the 5 added give you 8. The 5 and the 8 added give you 13. The 8 and the 13 added give you 21. 13 plus 21, 34. Fibonacci sequence. This one doesn't even have numbers. They're letters. So let's talk about, maybe skipping letters, or sometimes they stand for something. Maybe they represent people's names alphabetically in the class, or the days of the week, something like that. So let's look at this one, ECGIK. How many letters do we skip between C and E? A, B, C, D, E, F, G, H, I, J, K. We are skipping a letter in the alphabet between these. So what would be the next one? Say the alphabet in your head or out loud. J, K, L, M, N, O would be the next two letters. The last one is a picture. So what's happening each time? We're getting kind of like another line in the middle here. So we start out with a box, and we start out with one box with a box inside, and one box with two boxes inside. So now it's going to be the same size box to the best of your ability with 1, 2, 3 boxes inside, and then you would want to draw that picture one more time with this time 4 boxes inside. So next, example 2. Make and test a conjecture about the given quantity. So we're going to make a guess, and then we're going to kind of test it and see if our guess is true. So the sum of two negative integers. Pick some negative numbers, add them together, and see what happens. So negative 2 plus negative 3 is negative 5. Got negative 5. Negative 10 plus negative 1 is negative 11. So we got negative 5, we got negative 11 as our answers. Negative 1 plus negative 1 is negative 2. It seems like all of our answers, negative 5, negative 11, negative 2, whatever we got, they're all negative. So my conjecture would be this equals a negative integer. And we tested it by adding the negative numbers and getting negative answers. So let's hear the product of 3 consecutive non-zero integers. So this one I think I'm going to write out like 4 times 5 times 6. Let's do a negative 1 times negative 2 times negative 3. Maybe a 10, 9 times 10 times 11. And let's see what these are. And if you pick different numbers, it's okay. You're looking for integers, so whole numbers, and you want them to be not 0. So 4 times 5 times 6 is 120. Negative 1 times negative 2 times negative 3 is negative 6. 9 times 10 times 11 is 990. What do these three answers have in common? 120, negative 6, 990. You get an even answer. It's the only thing I can see here. The negative 6 means they're not all going to be positive, but they are all even. Example 3, find a counterexample to show that the conjecture is false. So we're looking for something that proves this is not true. So this says, if n is a rational number, rational means it can be a fraction, if need be, then n squared is always less than n. So let's pick a rational number and see what happens. Like n equals 3. I don't know, I'm just picking a number. If n equals 3, n squared n times n would be 3 times 3, which is 9. And this says that n squared is less than n. Is 9 less than 3? No. So when n equals 3, n squared equals 9, and 9 is bigger than 3. 3 is our counterexample. For B, line K intersects plane P at point Q on the plane. Plane P is perpendicular to line K. Alright, so this counterexample is going to be a picture. So here's a plane, and we're going to call it plane P. And we need a line that crosses at point Q. And this says that the line will be perpendicular to the plane, that they will cross at 90 degrees. So we just need to draw a line that does not cross at 90 degrees. And that should be line K. That's a counterexample. Now examples 1, 2, and 3 are important examples. At least 1 and 3 are typically on the final somehow. Example 4 and 5, though, are kind of the biggest part of this section. So use the law of detachment to determine what you can conclude from the given information. A. If a triangle has equal side lengths, then each interior angle measure is 60 degrees. Triangle ABC has equal side lengths. So what I want you to do is to circle the parts that come after the ifs and thens. So here, if a triangle has equal side lengths, we're going to call that P. Because on the front, it goes if P, then Q. If P, then Q. So we're going to use ifs and thens with P's and Q's. And we're basically deconstructing our sentence to say if P, then Q. Each interior angle measure is 60 degrees. If P, then Q. Now the question is, right here, triangle ABC has equal side lengths. Is that P, is that Q, or is that something completely different? Well, P says a triangle has equal side lengths. This says triangle ABC has equal side lengths. So, do you see has equal side lengths? Those words are exactly the same. The only difference is this one says a triangle and this one says triangle ABC. This statement here is just P. This problem, when it's all said and done, says if P, then Q. That's the first sentence. The second sentence is P. According to the law of detachment, if P, then Q, P, therefore we can conclude Q. So our answer, the conclusion, each interior angle measure is 60 degrees. In part B, we're doing the same sort of thing. If a quadrilateral is a rhombus, then it has two pairs of opposite sides that are parallel. Quadrilateral PQRS has two pairs of opposite sides that are parallel. So let's box some things in. P's and Q's. And I understand this putting boxes around, labeling the P's and the Q's, most students don't want to do it. But the students who do mark the P's and the Q's do significantly better than the students who choose to ignore what I'm telling them to do. So please, please, mark the P and the Q's. Here, if a quadrilateral is a rhombus, if, let's call that P, then Q, then it has two sides, two pairs of opposite sides that are parallel. Now you do not put the if and the then in the box. The if then are not part of what you're boxing in. Just the part after the if and the then. Now here, quadrilateral PQRS has two pairs of opposite sides that are parallel. Is that the P or is that the Q? P says a quadrilateral is a rhombus. This says nothing about a rhombus. Q says two pairs of opposite sides that are parallel. This underline says two pairs of opposite sides that are parallel. This is Q. So for this particular problem, it goes if P, then Q, Q. If P, then Q, Q. Look back up here. Law of detachment says if P, then Q, P. What's wrong with this? Well, what's wrong is that the law of detachment requires a P here, and this example has a Q. So what does that mean? It means there is no valid conclusion. Essentially, it's not law of detachment. We cannot use logic to actually make an answer. Example 5. Use the law of syllogism to write a new conditional statement that follows from the pair of two statements, if possible. So, if it does not rain, then I will walk to school. If I walk to school, then I will wear my walking shoes. What can we conclude, if anything? So again, we're going to box things in. We're going to put P's and Q's. So, if it does not rain, it does not rain is your P. Then I will walk to school. That's your Q. So if P, then Q. If I walk to school, is that P? Is that Q? Or is that a third one? Now I understand P, okay, P says does not rain. This says nothing about rain. Q says I will walk to school, and this one says I walk to school. They're not exactly the same, but they're basically saying the same thing. I will walk to school, I walk to school. The only word missing is the will. That's Q again. Then I will wear my walking shoes. That is a new statement. That's R. So for this particular example, it goes, if P, then Q. If Q, then R. If P, then Q. If Q, then R. So look at the law of syllogism. If P, then Q. If Q, then R. They're the same thing. So the conclusion is if P, then R. If P, then R. So now we actually have to write the sentence. You do have to actually put P and R back into the statement. So if P, it does not rain, then R, I will wear my walking shoes. Last one. If x is greater than 1, then 3x is greater than 3. If 3x is greater than 3, then 3x squared is greater than 9. Now this one, to me, my initial reaction is it's a little scarier because, like, this is math here. A lot of math symbols. We got stuff. We have an x. We have numbers. But you do the same thing. If p. I don't even really care what that look. We could totally ignore that and just say if p. Then q. If. Which one is that? P, Q, or R? That's Q again. Then, hey look, this one's new. R. If P, then Q. If Q, then R. The conclusion would be if P, then R. So if x is greater than 1, then 3x squared is greater than 9. At this point in time, you should have enough information to do your homework for section 2.2.